Today we're going to refresh the things that we know about complex numbers. So none of this is going to be anything that you didn't already see in Algebra 2. So we're going to do a quick little refresher of where imaginary numbers and complex numbers come into play. So if the real numbers was a giant set of numbers, then the complex numbers is another set of numbers. The real numbers and the complex numbers have no intersection. So you're either a complex number or a real number. And a complex number contains the imaginary unit I. And we have defined I to be equal to the square root of -1. The square root of -1 is not a value that we can actually evaluate. It doesn't exist. That's why we call it an imaginary number. Essentially what I does is it serves as a placeholder so that when I end up with the square root of a -1 somewhere, I can kind of hold it in place while I do my work and hope that eventually I'm going to be able to get rid of it. And that would happen when we end up with an I squared, because if I is the square root of -1, then when I square that, it undoes the square root and I get -1. So that's always kind of the goal. This was a really, really huge result in mathematics when someone decided, I'm going to make up this new number. I is made up. And it's allowed us to do a lot in the field of mathematics that we could not do before because we have this concept of the imaginary unit I. Okay, complex numbers are going to be written in the form of A plus BI. And that is always considered standard form. Okay, so standard form, whoops, this is not writing well, of a complex number is going to be always A plus BI. A is going to be the real number piece, and B is the imaginary piece, obviously. The BI contains the imaginary part. So if B was equal to 0, then A would just be a real number. But if A is equal to anything else, then you have a complex number because you have both a real part and an imaginary part. A could also be 0, and you could just have something like 2I, which is considered an imaginary number, but could also be written as a complex number. Okay, all the operations with imaginary numbers work exactly the same way as they do with polynomials or something like that. So adding and subtracting is essentially just combining like terms, okay? So for example, if I want to add 5 minus 11i plus 7 plus 4i, we're just going to combine the like terms that we have. So the two real pieces, 5 and 7, give me 12, and the two imaginary pieces give me minus 7i. And make sure that the I always comes last because that's the standard form of a complex number. Just like with polynomials, when we subtract, we have to distribute this negative. And so here we would end up with -10 plus 7i. So that's how we add and subtract. Multiplying gets a little bit trickier because we have to remember the fact that I squared is equal to -1. When we multiply I times I, we have to change the power. And that's helpful because that in some cases is going to get rid of the imaginary piece. So for number 3, we just want to distribute here 7i times 2 and 7i times -9i. So that's going to give us 14i minus 63i squared. Well, I squared is equal to -1. So this is really -63 times -1. So this comes out to 14i plus 63. But then again, standard form means that we have to reverse this. The real number always comes first. 63 plus 4i is what we get. And the hardest thing to remember when it comes to imaginaries is that that's not two numbers. 63 plus 14i is one complex number. Even though it has a real part and an imaginary part, that combination represents one complex number. All right, number 4, we can use the idea of FOIL here just the same way. So 5 times 6 is going to give us 30. then our outside and our inside is negative 35i, and our inside is 24i. And again, you can keep track of that in your head if you want. When I combine those together, I get negative 11i. And then our last is 4i times negative 7i. So we get negative 28i squared. Now remember, negative 28i squared is going to be negative 28 times negative 1. So this is really just going to be positive 28. And so when we combine, we get 58 minus 11i. And so that is our complex number. Okay. Now, division is where it gets a little bit tricky, and this word conjugate is a word that we've heard before. Remember that when we were talking about multiplying polynomials and factoring polynomials, we said anytime we multiply a plus b times a minus b, those are called conjugates, and the result is always going to be the difference of two squares, a squared minus b squared. Well, because if I add in the I values there, so you see here we have a plus bi, a minus bi, or vice versa, what we're really getting there is a squared minus bi squared. Well, that's a squared minus b squared I squared, and we know that I squared is negative 1, so that's why this turns to a squared plus b squared. If all else fails, you can always just use your FOIL or your distributive property and multiply that out. But if you remember, complex conjugates end up giving you the sum of two squares, which, remember, we said is not factorable using real numbers, but we can do it using imaginary numbers. So when we divide complex numbers, it's very similar to the idea of dividing radical expressions. We have to eliminate the complex number from the denominator. And the only way that we can do that is by multiplying by the conjugate, because we want no i's left in the denominator. So the only way to get rid of the i's is to use this idea up here. Notice that after you've multiplied, there are no i's left in that expression. That's the whole point. That's why we choose to multiply by the conjugate. So you're always going to look at the denominator. The numerator does not matter. And we're going to multiply by the conjugate, which would be 2 plus 5i. You just switch the sign. And if we do that on the bottom, we have to also do that on the top. Now, right away, I know that the denominator is going to become a squared plus b squared. So that's going to be 4 plus 25. B is just the 5. It's not the I. B is the number in front of the I. So, ta-da, there's no more i's in the denominator. On the top, we need to multiply that out. So we'll get 14 outside, inside, 35, and 8. So this is going to be plus 43i. And then we're going to get plus 20i squared. Now, we know that 20i squared is going to be negative 20, because I squared is negative 1, so we can replace that. And then we can combine our terms in the denominator, so we should end up with negative 6 plus 43i over 29. Now, this would be an acceptable answer unless we are looking for the answer in standard form, which typically we are, okay? If it is in standard form, we need to split it apart so that it has the real part and the imaginary part. So that would mean we need to write this as negative 6 over 29 plus 43 over 29i. And that's how your answer will be expected to look in my math lab. If it says standard form, it's got to be written as a plus bi, which means two separate terms. Now, you should always check here and see if anything can be simplified. And in this case, neither one can. So that's just our answer. So will you put the video on pause, take a second to kind of process that, and try number 6, multiply by the conjugate. Again, we want to look at the denominator, decide what to multiply by, and come back in 3 seconds for the work and the answer. All right, so again, we're going to multiply top and bottom by 4 plus I over 4 plus I. When we do that, our denominator is going to be 4 squared plus 1 squared, because that's the coefficient of I. So that's going to be 16 plus 1. And in the numerator, when you FOIL, you should get 20 plus 21I plus 4I squared. Knowing what we know about 4I squared, we know that's negative 4. And so we can combine, and we're going to get 16 plus 21I over 17. And we split that apart to be 16 over 17 plus 21 over 17I. And there's nothing that we can simplify there. Sorry, this got moved down too low for you. And so that is our final answer. Okay, taking square roots of a negative number. The way that we get rid of the negative is with an I, because we're breaking this down into the square root of negative 1 times b. And so we're going to use our other simplifying processes just exactly the same. So for number 7, I definitely can split this in the following way. I'm going to have the square root of negative 1 for sure. And then I want to think, what's the biggest perfect square that goes into 27? That's going to be 9, and it's 9 times 3. So that's the product of radicals we want to look for. We can replace this one with an I, and we can replace this one with just the number 3. So this will become 3I root 3. We want to do the same thing with negative 48. We know that we have a negative 1, and then 48 is going to be 16 times 3, square root of 16 times square root of 3. This can be an I. This simplifies to 4, and so we're left with plus 4I root 3. Now these are like radicals. They're both a square root of 3, so that means we can combine their coefficients, and we get 7I root 3, and that is your final answer. The standard form may want you to write it like this. I don't like that. That might be what my math lab wants, but it gets very confusing whether the I is under the square root or after the square root. We usually keep the I in front of the radical. Okay. Number 18, or 8, we are squaring a binomial, so it's the same process as what we've done before. Square the first, negative 2 squared is 4. Square the last, that's going to cancel out the square root, so we're just left with negative 3. Multiply and double, we're going to get minus 4 square root of negative 3. And to simplify from there, we get 1 minus 4I root 3. The I comes from this negative right here. Okay? And that would be our answer. The 4 minus 3 is where the 1 comes from. And then on number 9, we get negative 14 plus the biggest perfect square that goes into 12 is 4. This is 4 times 3. And since it's negative, we're going to get an I. The square root of negative 4 is going to be 2I root 3 over 4. Now again, just like when we did the quadratic formula, we can only simplify if we're able to divide all 3 terms by the same number. And we can divide them all by 2. So we get negative 7 plus I root 3 all over 2. And don't forget standard form, we have to split it apart. So this would be the square root of 3 over 2I is how we would write that in standard form, okay? I know it was a little fast. If you need to pause the video and kind of work through those again in your mind and make some sense of that, then go ahead and do that now. We're going to do the last 2 examples here. Okay, the last, or just one example, is that now this opens up the possibility when we solve our quadratic equations that we might have imaginary solutions. So I would like for you to pause the video and do this problem using the quadratic formula and see what you end up with. I'll come back in 3 seconds. All right, so this is what you get when you do your substitutions and start working that out. And hopefully you notice there that now we have a negative under our radical. So this is going to become 2 plus or minus 2i over 2. And since we can divide all of those things by 2, the solutions we end up getting are 1 plus or minus I. And so using a set in my math lab, we would say 1 minus I and 1 plus I. And so there you go. Same process as solving as always, but now you might end up with imaginary solutions, and we need to be able to account for that.